Well, welcome to the 6.5 notes. We're going to be looking at complex numbers in polar form. We're also going to look at one more graph of polar curves, a graph called lemniscates, and that'll be right at the end of these notes. But let's just start off with complex numbers. So a complex number is the sum of a real number and an imaginary number. You actually worked with them before in Algebra 2, and it was common for complex numbers to be described in this format, a plus bi. So you may have had something like 3 plus 4i, something like that. And you would do operations with them, add, subtract, multiply, divide, rationalize, and you may have even graphed them a little bit. So let's say that we call a complex number z, and the rectangular form, or the form that you're used to with the xy, would look like this, a plus bi. But our coordinate plane is a little different than the x-axis and the y-axis. We're changing it instead to a real axis and an imaginary axis. So A would be how far over we are on the real axis, and B would be how far up or down we are on the imaginary axis. And BI would tell you that that's the imaginary component of that complex number. And so one of the things we'll be dealing with is we want to make sure we know what the absolute value is of a complex number. This is also called the modulus. This is going to look super familiar. This is like the same idea as magnitude. It's the same idea as the radius. This would be basically the length from here to here. The length from here to here is the absolute value of that complex number. It's also, again, called the modulus. But this is the same idea as magnitude, same idea as radius. It'd be the square root of those components, both the real component and the coefficient of the imaginary component. So the square root of a squared plus b squared. So when we're talking about the polar form of a complex number, we want to show you where it comes from. So on the next page, we'll actually look at the polar form, but this part, we're just going to derive it one time. You won't have to go through this process every time you work with a polar number, a complex number, and you try to write it as a polar form, but this is just one time. So here's kind of an example. Let's say we're looking at the complex number 4 plus 4i. I'm going to start by plotting this on the complex plane, where again, the horizontal axis is the real axis. My real component is 4. And then my vertical axis is the imaginary axis, and my imaginary component 4i would be up, positive 4 as well. So this is the location of z. So if I want to find the absolute value of z, or the modulus of z, which would basically be the length from the origin to point z, I'll just do the Pythagorean theorem of 4 squared plus 4 squared, which is square root of 13, or 4 root 2 if you simplify that number. If I wanted to find a polar coordinate for z, I would start by finding r. And what we would find out, essentially, r, remember, is the length from the origin to a point. And so the absolute value of z, or the modulus of z, could also be called that radius of r. So it's the same thing. This is the same thing. Instead of using x and y, we're using a's and b's, but it's the same thing. And so r is 4 root 2, just like the absolute value of z, or the modulus of z, is 4 root 2. What we're going to do now is we're going to use some substitution to write this in polar form. Now, in the past, we've said x is r cosine theta, but now our horizontal axis has been renamed to the real component. We're going to call that a. And then the vertical component, instead of calling it y, we're calling it b, and that would be r sine theta. And just like before, theta is going to be the inverse tangent of b over a. So what I'd like to do is to write this in the form a plus bi. Well, a is r, which is 4 root, so in other words, this would be 4 root 2 times the cosine of theta, plus 4 root 2, I'll just put I in front of the trig function just so that I don't get confused about what the argument is, 4 root 2 I sine theta. That's essentially what we're going to do, but we are going to need to figure out what theta is. Remember, r is, for both of these, 4 root 2. So the question is, what is theta? Well, theta is going to be clearly in the first quadrant. Remember that we measure it from that normally it's like the polar axis, but with the x-axis right there, that positive side of the x-axis, we're going to go counterclockwise if we want a positive angle, which is the most common way to write this. So theta is the inverse tangent of b, which in this original problem is 4 over a. So in other words, theta is going to be found by taking the inverse tangent of 1. So what is the angle in the first quadrant, where when you divide sine divided by cosine, you get a 1 because the sine and cosine are the same? Well, that would be pi over 4. So we could say that the polar form for z, I'm going to remove these parentheses. I don't really mean anything. I'm not really 100% sure why I wrote them in there. But that polar form then for z, remember this was the rectangular form. This is going to be the polar form, would be 4 root 2 times the cosine of pi over 4 plus 4 root 2i times the sine of pi over 4. Now, by the way, if you calculated the cosine of pi over 4, you'd get root 2 over 2. That would simplify to this 4 right here. 4 root 2 times root 2 over 2. That's going to all simplify out, and we would get back to the same answers. So this is the polar form to get us back to the 4 plus 4i. By the way, this could also be written where we factor out the GCF, which is essentially r. Both of these are multiplied by r. So I could factor that out, and I could get 4 root 2 times the quantity of the cosine of pi over 4 plus I times the sine of pi over 4. Now, just to kind of check this, make sure that this works, I'm just going to expand this out back from here. This would be 4 root 2 times root 2 over 2 plus 4 root 2i times root 2 over 2, because that's the sine and cosine of pi over 4, which is this right here is 4 times 2 divided by 2, which is back to 4. And same thing here. And notice we get the same thing. So these are equivalent. This was the rectangular form. This was the polar form. I prefer the factored version. You'll see why when we get to the next page. We're going to have a shorter way to be able to write this, which is awesome. So that was the derivation of what we're going to look at next. The polar form of a complex number can be found by writing that complex number as z equals r cosine of theta plus r sine of theta times I. Or we could take that common factor of r and factor it out as a GCF. So we'd have z is r times the quantity of cosine theta plus I sine theta. We'll just move that I into the front so that it doesn't get confused. Is that multiplying theta, or is that multiplying the whole function? It's multiplying the whole function. And even better is this form, r cis theta. What the heck is cis? This is the first initials of cosine, imaginary number I, sine. So this notation is commonly used when we're talking about the polar form of a complex number so that we don't have to write as much. It is shorthand for cosine of theta plus I sine of theta. And so it's pronounced cis theta, and we could substitute in an angle there. And then that would give us the equivalent form to the rectangular a plus b sine theta. So here's an example. Example 1, we're going to take z. We're going to start by plotting it in the complex plane. We're going to write it in its polar form, and we're going to express its argument in radians. Okay, so I'm going to remember that the horizontal is the real, the vertical is the imaginary axes. So I'm going to do -1 minus I root 3. Well, root 3 is like -1.7-ish, so I'm thinking like here-ish. There's where I think z is. So to write this, I'm going to write this in the form r cis theta. Remember, cis is really cosine plus I sine theta. So what's r? R is going to be found from the Pythagorean theorem with the real component of -1 and the imaginary component of negative I root 3, but I won't use I. I'm just going to use the coefficient of that. And so I really went down like -3 in that imaginary portion. Okay, there we go. So this would be 1 plus root 3 quantity squared is 3. The negatives cancel out. R is the square root of 4, or 2. And the next thing I have to find is what is theta? What is theta here? As I figure out where is the placement of this, starting from the x-axis. So I want the inverse tangent. So theta can be found by doing the inverse tangent of, we'll use b over a, imaginary over real, y over x, lots of different ways to think about this. This is like negative root 3 over negative 1. Now I want to kind of relate this back to my unit circle, so I might want to think of this as negative root 3 over 2 over negative 1 over 2 to kind of help me figure out where this would be. So the y component would be negative root 3 over 2. The x component would be like a negative 1/2 if I'm trying to figure out this angle. So this right here is a pi over 3 angle. And the pi over 3 angle that's in the third quadrant would be 4 pi over 3. So the reference angle here, that angle is pi over 3, but we're going to use 4 pi over 3 so that we're placed properly in that third degree angle. So z could be written a lot of different ways. It could be written 2 cosine of 4 pi over 3 plus 2I sine of 4 pi over 3. But the fastest way to write this is r, which is 2. And then cis for a cosine I sine of the angle. These angles will be the same every time, which is 4 pi over 3. And that's going to be the fastest way to write this number in polar form. Now, in example 2, you're given the angle already in its polar form, and now we're working backwards to find it in its rectangular form. So essentially, we're just going to evaluate this. So this time the angle's in degrees. A little less common for it to be in degrees. Most of the time it's going to be in radians. But let's think about what we know about a 30-degree angle. In the 30-degree angle on the unit circle, the cosine would be root 3 over 2, and the sine is 1/2. So this would be 4 times the cosine of root 3 over 2. And this 4 distributes, so plus 4i times the sine of 30, which is 1/2. I'm not really sure why I kept the cosine. Let me rethink that. That looks a lot better. So this would become 2 root 3, and then 4 times 1/2 is 2, and I is still multiplying that. So this would be z in its rectangular form, a plus bi. So when you're going from polar to rectangular, you basically are just evaluating. You're just evaluating and multiplying that out. We don't write the rectangular form in cis anymore, so notice how I distributed that and evaluated that. All right, there are some operations we can do with complex numbers in polar form. They're easy. So it's kind of nice. We're ending up this unit on an easy section. When we multiply them, interestingly enough, let's say we've got 2 complex numbers. Maybe one of them is called z and one of them is called w. They each have their own radius. They each have their own theta angle. We'll call them radii 1 and 2, and then theta 1 and theta 2. So what you do when you're multiplying is you take the radii and multiply those. So make sure those get multiplied. And the angles, the different theta values, we add. So that's interesting. This kind of reminds me a little bit of like how when we're dealing with exponential functions or exponents, how exponents are going to be added together when with logarithms, how when we condense and expand, how multiplication and addition kind of switch out. Same thing here. When you're dividing, it's very similar. We'll take the various radii and we'll divide them. Whichever one we're dividing first would go on the numerator. And then for those arguments, we'll subtract them to get a new argument. So example 3, we want to find the product. There we go. We're going to find the product. Z sub 1 is 6 cis 40. Z sub 2, 5 cis 20. So if I want to find the product of z sub 1 times z sub 2, I'm going to take the radii of 6 and 5 and multiply them together. And then I will take the angles for their arguments and add them together. Okay, so that 30 came from 5 times 6, and that 60 came from 40 plus 20. We're just going to add those arguments together. Example 4, and again, we're leaving these in polar form. I'm going to find the quotient of z sub 1 and z sub 2. And so when we say it this way, the first one listed is the numerator. So z sub 1 over z sub 2. I'm going to take the radii, those will get divided, and then cis, and I'm going to take the arguments, and those would become a subtraction. Division would become subtraction. Think about like condensing and expanding when we're talking about logs. Very similar. All right, so I'd end up with 25 cis, and then let's see, 4 pi over 3 minus 1 pi over 3 is 3 pi over 3, which is pi. And that's in polar form. The last kind of part here before we look at one more polar graph, de Moivre's theorem. We're going to let z equal r cosine, basically r cis theta. That's going to be some complex number in polar form. And if n is a positive integer, if we want to take that complex number in polar form and raise it to a power, here's how we could do that. We could take the radius and raise it to the exact same power that z is raised to, the whole number. And then we take the argument, whatever theta is, and this time we multiply it by n. So all of these are like one step down. Whatever operations in the front is the operation that we're doing. Whatever operation to the argument is like one step down. One step down from powers would be multiplying. One step down from multiplying is adding. One step down from dividing is subtracting. So for number 5, we're going to write this in polar form. We're taking this to the power of 5. So the radius in the front would be taken to the power of 5. And then cosine plus I sine theta, I will abbreviate in shorthand as cis. And then I will do 5 times 30. I'm not taking the 30 to the power of 5. Oh, and this is still in degrees. So I'll get 32 cis 150 degrees. And since I'm not in radians, you should use the degrees symbol because degrees are unit. Radians don't have a unit, which is why we don't write a unit with them. Okay, example 6. We are going to start with 1 plus I raised to the power of 4. You might notice this is in a rectangular form. I'm not using cis. This is not polar. This is a rectangular, if I can spell, form. This is a plus bi. Using de Moivre's theorem, we're going to write my answer in rectangular form as well. Well, de Moivre's theorem, though, is written in polar form. So what this means is that I have to first write this in polar form, use the theorem, and then I need to go back and write it in rectangular form. So I kind of have to do some converting first so that I can use de Moivre's theorem. So I'm going to draw a picture of this complex number using the real and imaginary axes of the complex coordinate system. So I'm going to move over 1 in the real and up 1 in the imaginary. This is where point Z is at. Since I want to write this as a polar, when I write this as a polar, I'm going to write Z in the form r cis theta. To find r, I'll use the Pythagorean theorem with the real and imaginary components. 1 squared plus 1 squared is going to be the square root of 2. And then I need to also find the angle measurement of theta. Well, theta is the inverse tangent of 1 over 1, so I need my sine and my cosine to be the same to reduce out, so theta must be pi over 4 since I'm in the first quadrant. So this would be root 2 cis of pi over 4. And I now want to take this, remember this is essentially z, I'm essentially finding z to the 4th power, that's what I'm doing. So if I used de Moivre's theorem, z to the 4th power would be root 2 taken to the 4th power, and then cis, and I want to take my argument and multiply it by that power of 4. So root 2 to the 4th power would be root 2 times root 2 times root 2 times root 2, which is 4. And then cis of pi. That's what z to the 4th is. But for my final answers, this is in polar form. I want to write it in rectangular form. So I'm going to expand out, I'm not going to use the shorthand here, of this polar form, and then I'll just evaluate it. So this is 4 cosine of theta plus 4i, remember that's what the I and cis stands for, sine of same angle, same argument. Well, if we think about where the angle theta or pi is, the ordered pair is -1, 0. That's your cosine and your sine. So this would be 4 times -1 plus 4i times 0. So we could write z to the 4th as -4 plus 0i. You can definitely write it like that. You could also just write it as -4. What we would find out is that this ends up being a real number answer here. We don't end up with an imaginary component, so it's no longer complex. All right, we are at the very last part of this. We have an exploration. We're going to look at the polar equation r squared equals 9 cosine of 2 theta. So the first thing, how is this different than a rose curve? How is this different than a rose curve? Rose curves would look like this. R equals a times the cosine of n theta, or r equals a times the sine of n theta. But what they don't have is they don't have the r squared. And so we are going to have a picture that looks different. You're still going to see some similarities. You're going to see some petals. So let's say we wanted to graph this on our graphing calculator. Well, we can. And remember, our graphing calculator will allow us to do polars. We have to make sure we've got everything set up properly. We want to make sure that in our mode, we have radians rather than degrees and polar instead of function. By the way, if you ever want to go back to normal graphing, what you would need to do is you would need to go back and highlight function. And if you wanted to do that and you went back to up here, you notice it says y equals. But if I want to do polar, this is where I would change it. And then when I graph, you'll notice, this is from the cardioid that we did in the 6.4 video. So, okay, now what I want to do this time is I want to be able to graph this, but in my calculator, it just says r. It does not say r squared. So I need to isolate r. So I'm starting off with r squared is equal to 9 cosine of 2 theta. But I need to isolate r, so I'm going to go ahead and square root both sides. As a reminder, when you take both sides of an equation to an even root, you get two solutions. You get a plus or minus. So r is equal to the positive or principal square root of 9 cosine of 2 theta. By the way, you could square root 9 and make it a 3 since it's a constant multiplier. Only when it's multiplying or dividing can you do that. R is also equal to the negative square root of 9 cosine of 2 theta. It's equal to both. So if I wanted to graph this, technically I could put in both equations into this expression. I'll graph the square root of 9 times the cosine of theta. And I'll also graph the negative square root of 9 times the cosine of theta. Again, I could have taken that square root of 9 and put it as a 3 outside the radical. That's up to you. You're welcome to do that. I just didn't feel like bothering. I guess I can close that argument. There we go. Now, when I graph this, I should get a picture of these. I might have to adjust my scale. I don't remember what I last had on here. Now, this is a little bit imperfect. Here, I'm going to see if I can change my window to kind of accommodate this. I'm going to make my x's maybe -6. Maybe I'll make my y's -4. Let's see if I can see a little bit better what's happening around the origin. Not really. Okay, so this graph has some imperfections here. This calculator is pixelated. And so because it's pixelated, it's really hard for them to kind of show you what's happening here. Let me see if I can switch over really quickly to Desmos. Let me get a Desmos. Let's see if I've got one in here. Or maybe I could do r equals the square root of 9 cosine of 2 theta. And I'm going to do this to the power of 1/2. Doesn't like what I'm doing, so I must be entering something in wrong, but let's see what happens. Take that one off. And see if I can turn that one on. All right, it does not like it. I did something wrong here, probably how I defined r on this. So, okay. I'm not going to be able to graph it on that, which I apologize for. Here's what it ends up looking like. Sorry, I thought when I graphed it on a different calculator before and it worked better. But this is what it ends up looking like, which we can kind of see. I'll go back to this one a little bit. What happens is right in here, it actually dips back down to the 0. Right in here for both of them. It kind of ends up looking like an infinity symbol. So we're going to go out 3 units because the square root of 9 is 3. And it's going to be along the x-axis, which might make sense. It's cosine. And it has 2 petals instead of 4, and that's because of the r squared and the square rooting. What ends up happening is that these 2 graphs actually end up being the same graph. And they kind of just trace along each other twice. And it's like this infinity symbol along cosine, which is interesting. Actually, this one says just graph your first and then graph your second. Let's explore that really quickly. Let me take off this one. I'm going to delete this one. And so if I only graph the first one, let's see what happens. Oh, there's that. And if I graph the second one, I guess that did give me the negative. I'll copy this on here again. That gives me that other side because we'll get a negative for the cosine, and that's how I'll get the other side of the graph onto the negative axes. All right, so what we hopefully can notice is that there is symmetry here in a couple ways. First of all, along the x-axis. That's because this is a cosine graph. And then also the left and right sides are the same. And that's because we have the same equation but opposite signs. Now we're going to do a sine function. So I'm going to do the same ones. I'm just going to change this to sine. If I isolate r in this equation, I would have to square root both sides. And again, I'm taking an even root. So I'm going to get 2 answers. R is plus or minus would be a compact way of writing this. The square root of 9 sine of 2 theta. So if I graph this, I'm going to just change these trig functions from cosine to sine. Oh, hang on. Maybe that's what happened. I think this is why my graph didn't look right. I just didn't type it right. Let me go back to the cosine graph and see if it now works the way it should. I'm going to change this back to cosine. I didn't even notice I typed it wrong. Hopefully we'll get the good picture now. There we go. Still have some issues with pixelation. This does connect right here, but you can kind of see more of that infinity shape. Now I'm going to change this to sine for both of them. This one was able to graph the whole shape, so we didn't have the issues with pixelation. A little bit right in here, they're kind of having a little trouble with that. But there's the infinity sign. This is interesting, though. This one's not along the y-axis. This is like going right through kind of the 45-degree angle, which is very, very interesting how it's doing that. So it's still going to go out 3 units, 1, 2, 3, but the petal for each kind of the infinity symbol will be right along the 45-degree angle. So it looks like that, essentially. And that will always be true. The sine ones will always be kind of in that first and third quadrant. The cosine ones will always be right here along the x-axis. We're only doing 2 theta for lemniscates like that, and they always have that r squared. To find out the length of the petal, it's going to be the square root of whatever number is in the front. So like for these ones, the length of the petal is 5. 1, 2, 3, 4, 5, because that's the square root of 25. Same thing no matter what direction you're going in. Okay, the last part here, this will be important. You'll see something similar to this on your test. We're going to match each polar equation to its graph without using a calculator. So we have to be able to look at the forms and tell what they mean. So there's a couple circles on here. These first 3 are all circles. Number 3 is a circle centered at the origin. That's going to be letter B with a radius of 4. That's what that one means. 1 and 2 are also circles. Number 1 is along the y-axis, the positive side. Number 2 is going to be along the negative side of the x-axis. And the numbers in front are the diameter if we disregard the negative. So let me start by finding a circle along the y-axis with a diameter of 3. And so that looks like H. Is that one? Number 2, I want a circle that is along the x-axis, the negative side of the x-axis with a diameter of 4. That is I. Number 4, this is a cardioid. When A and B are the same number, they can have different sides. Let me see if there's any other cardioids in this set of equations. I see one right here. A and B are the same number. I think that's it. Those are the only ones I'm noticing. So both of these are cardioids. Number 4, those cardioids are along the x-axis because this is cosine. So I want a cardioid, that heart-shaped graph. Cardioid should always have the point of the heart or the dip of the heart at the origin. And it should be along the positive side of cosine. So letter K. If I look at 13, this is also a cardioid, but this cardioid is along the positive side of the y-axis. So I'm looking for that heart along the positive side. Again, make sure that that goes to the origin. So that is letter O for number 13. We just looked at lemniscates, and I see a couple on here, right here. The cosine, so these are your infinity-looking graphs. Cosine is along the x-axis. Sine would be along kind of like the first and third quadrants. You can see I had trouble graphing it a little bit. It just looks kind of funny when you graph these just with the pixelation. That's letter N. Okay, I've got a couple more limacons. So when you're trying to decide between the limacon with a dimple or an inner loop, here's what you can do. Decide, would I ever go into the negative? Remember that the most that sine and cosine could be would be a -1, or the least it could be. So would this number 5 have me go into the negative? The answer is yes. This would go into the negative if sine is -1. So this one must have an inner loop. And because it's a sine function, this should be going along the y-axis. So I should have an inner loop, and I should be going along the y-axis. This would be letter E. And I want to see, is there another one that could go into the negative? Keep in mind, the most cosine could be as 1, the least it could be as -1. So where would we potentially dip into the negative? And that'd be number 15. This one also has an inner loop, because if cosine of theta has an output of 1, we'd get a negative. So this is a limacon with an inner loop, but it should be along the x-axis. Sorry. A limacon with an inner loop along the x-axis, that's going to be M. If you're wondering, why is this one like along the negative side of the x-axis? It's because of the minus between the signs. So we have a couple others in the form of limacons where we're like adding things in here. And so this one's another limacon, but this one must be with a dimple, because no matter what I put in for sine, if I can get 1 or -1 is the most extreme values, I'm not going to dip into negative. I'm also never going to be able to get to a 0, because 3 + 1 or 3 - 1 will never get me to a 0. So this must be a limacon with a dimple, but it's along the y-axis since this is a sine graph. So that's what I'm looking for, and I see that with J. Notice it's not quite a circle. It is just a little, it's sometimes hard to see the dimple. Sometimes it flattens out pretty good, but that's going to be letter J. And also, too, you could tell, like, if we put in a pi/2, that'd be a 1. 3 + 1 is 4. The most we should get to is a height of 4. And if I put like 3 pi/2 in for sine, I'd get a -1. 3 - 1, the least I would get is to a -2. There should be one other that has a dimple. That's number 6. And so I would like this to be along the cosine graph. That's going to be option D. So the rest of these are Rose curves. The Rose curves are going to be the ones that have that multiplier of theta, but not the squared that the lemniscates have. So we wouldn't have the r squared. So when we're looking at number 7 has 4 petals, as does number 8. In fact, these both have 4 petals with a length of 3. So we really have to differentiate, and here's what we should know. For any with cosine, at least one petal will be along the y or along the x-axis. And if they have an even number of petals, it'll actually be 2. But that will always happen. So I'm looking for 4 petals, and we need to have at least one of them along the x-axis. And so that would be option A, because these 2 petals are right along the x-axis. That's A. I'm not sure why I crossed that out. There we go. Number 7 would be the other one with 4 petals, but we should have none on the x-axis. Now, sometimes with the sine rose curves, you will have some along the y-axis, but it usually only happens, I think it actually only happens if you have an odd number of petals. So this one is G. So 11 and 12 are also rose curves. They each have 3 petals. If n is an odd number, the number of petals is the same as n. And again, cosine should have at least 1 petal on the x-axis. So if I check for cosine right along the x-axis, I'm looking for that 3 petals, 1 of them along the x-axis. This would be letter L. So the only one that's left should be another rose curve, 3 petals, and with sine, if there's an odd number, one of them will be along either the positive or negative part of the x-axis. So this one must be letter F. So hopefully that was a good review of what we did in 6.4. And that is the end of the notes for this unit.